mass 56 are larger than standard material. And these values vary, ranges from 0.036 to 0.66. And this is an example of excess heat generation. And time and excess heat is plotted. At this point, making up the current up to 3 amperes, we obtain the excess heat like this. This dotted line is a 3 sigma. Next figure shows the example of X-ray emission. Upper figure is total time and X-ray counts. The average value is different because X-ray tube, or the detector of the X-ray tube, has a large size crystal of ENEA, and this one has a small size of crystal. But the coincidence X-ray 2 and X-ray 3 is very good. If we magnify this period, we obtain this figure. Time and X-ray 2 and X-ray 3. We can see the coincidence of X-ray 2 and 3 is very good. And I will explain about the SIMS results. Here, let's show the result SIMS analysis of FE standard material. Horizontal axis is depth. These are depth profile. And secondly, ion intensity is isotopic abundance ratio. We see but for the EV53, we have anomalous distribution like this. A depth profile, and secondly, ion intensity and mass number ratio. This material, this sample, with this sample, we observed excess heat and X-ray. Especially mass 57 by mass 56 behave anomalously. It reaches to average value 0.45. If we consider about the FE standard, average FE 57 by 56 is 0.023. It is 10 times, more than 10 times larger. And other points, at the other points of the same sample, we analyze the SIMS analysis, and we also anomalous distribution. In this case, mass 57 by mass 55 reaches to about 0.9, very high value. And average mass 57 by mass 56 is 0.66. On the other hand, background data, EV54, it is used in the right-world experiment, distribute uniformly like FE ion standard. And average mass 57 by 56 is near to the FE standard. Now we discuss on the mass 57 by mass 56 and ion 57 by ion 56. Mass 57 by mass 56 is defined as this expression because the candidate for mass 57 is Fe57, FeH, and COH, and the candidate for mass 56, Fe56 and CaO. And these elements, these are the value of secondary ion intensity, so they are positive. The term, every term is positive. And if we substitute the value of EV50 belongs to match layer cathode, we can get this relation. And we obtain the Fe57 by Fe56 larger mass 57 by mass 56 minus 0.072. It is supposed the calcium oxide, the factor of calcium oxide is the same as EV54, EV50. So we can estimate minimum Fe iron 57 by iron 56 is shown here. So we can see in the case of EV52, these are the various anomalous values. So we consider that the ion detected on the match layer cathode cannot be explained by contamination. So concluding remarks. A new type of experimental apparatus is developed to induce nuclear reactions by continuous diffusion of deuterium. Titanium atoms were detected on the surface where deuterium atoms pass through on the PD cathode after electrolysis. Quantitative discussion shows that the detected titanium atoms cannot be explained by contamination. A multi-layer cathode is introduced based on an electron-induced nuclear reaction model. Excess heat generations and X-ray emissions were observed for all the times we tried by multi-layer cathode. Fe57 by Fe56 ratio of detected Fe elements on the multi-layer cathode are enormously large in some cases. Thank you.
Open for discussion.
Were you able to get an X-ray spectrum?
X-ray spectrum?
I would stop at these three
X-ray spectrum?
questions.
Because excess counting is very low, so it's a low level count, but we get the X-ray spectrum shown here. This figure shows the X-ray spectrum average per channel. Solid line, the X-ray 3 count and dotted line X-ray 2 count.
Do you have a background?
Of course, we have a background for light experiment water, but now I do not have the background spectrum.
How many experiments is your conclusion number 5 based on? How long have you run these experiments? Your conclusion was the reproducibility. You always find this.
How long? How many times? About multi-layer cathode, only 5 cases.
My name is Scott Little from Earth Tech. First, I'd like to congratulate you for presenting analytical results on standard reference materials side by side with analytical results on your samples. Second, my question concerns the calorimetry. I noticed in the photograph the apparatus does not appear to be insulated, thermally insulated.
Yes.
What is the typical heat recovery? What fraction of the input power do you recover in the mass flow?
Okay. Typical heat recovery is about 92% or so. Not so high.
Your excess heat results are what percentage of the input power are they?
Yes.
What percentage?
Maximum value is about 10%.
Last question.
Tom Passell, retired. I congratulate you on the most beautiful paper. I was quite impressed by it. I wondered if you had calculated from the amount of excess heat that you produced, how much titanium and iron you might have produced, say, by the fission of one of the palladium isotopes.
Excuse me, your point is...
Well, I wondered if you tried to calculate, based on the amount of titanium
yes.
represent if it were formed by the fission of palladium isotopes?
We calculate the excess heat on hydrogen atoms. Excess energy by atoms is about 2 megaelectronvolt or 3 megaelectronvolt per titanium atom.
I can talk to you later.
Excuse me.
Okay. Let's start again. Next speaker is Dr. Swartz. Energy technology, from energy technology. The title is Comparative High-Notch Optimal Operation Point Characteristics of Solid-State Nuclear Systems.
Happy Earth Day. What we're going to discuss is the possibility of the presence of an optimal operating point for nickel light water systems. We've examined several materials in several forms of nickel: wires, rods, spirals, plates, mesh, fiber X screens, as well as multiple cathodes in a parallel opposed configuration with various plates of iron, nickel, graphite, and other materials. Our system is driven by an electric current source, and in terms of the calorimetry, which I'll go over in a few minutes, we use a static system with low heat loss. We've observed for nickel light water the presence of excess heat in range of 7 watts per cubic centimeter, and 88 milliwatts per square centimeter of nickel. These observations are greater than the noise power, and I'll show you that shortly. We have found them to be fairly reproducible, but more importantly, the excess heat only being present over a relatively narrow portion of the input energy. In our experimental setups, we began by investigating several types of thermometry. I'll go over that shortly. In order to test the calorimetry, we do thermal waveform reconstruction, where we put in the ohmic control a square wave, and we want to make sure with our calorimetry that we are then able to derive an identical signal. Various other studies were done on the electrodes following the driving them in the cell, including conductivity studies and testing for residual radioactivity. We've electrically driven the electrodes between 20 microamperes per square centimeter up to the levels indicated here. When we calculate whether there is the presence of excess heat, in the denominator, I do not use the thermoneutral potential, but just V times I, nor do we add anything to the numerator in terms of exit stream loss. Therefore, our calculations would be a lower limit to any possible excess heat. In the initial thermometry study, we looked at over 30 types of probes and chose those for optimal linearity, accuracy, and precision, and ditched the rest. We ended up getting down to accuracies and precisions as noted on the chart. We've tried very hard to have delta T's a minimum of 20 degrees, and as you can see here, we try to have very long initial baselines. What we have here are 2 cells here, and we put in between ohmic controls, and I'll talk about the other controls shortly. And here you can see we have a fairly large delta T. We try and use redundant thermometry within the electrochemical cell, often as many as 6 probes in each ring. I'll tell you what that is in a moment. And we also use redundant systems as a way of monitoring temperature so that we can be more certain of our calorimetric calculations. As I say, we use a multiple ring system, which looks like this. The cell is here in the center. Here you see a cathode spiral, and here there are 2 parallel opposed platinum plates. This is the inner ring. We have a second ring on the outside and subsequent rings. We use feedback control on the outer rings, but leave what's typically called back unclamped, and we actually watch the temperature rise. That allows us to watch the energy move from the electrochemical cell out towards the environment. Here's a picture of the setup with the yellow springs controller used to control the 4th loop. All these wires are going to various thermometry systems that we use. And on the other side of the system, we use multiple computers as a way of calculating the temperatures and putting them onto record. Our sampling is as fast as 10 per second. We've tried recently to get differential temperature measurements across the electrochemical cell. I'll show you the results of that shortly. We were able to look at the vicinal temperature of the cathode and the anode, and you'll see why that's important shortly. In terms of controls, in addition to an ohmic control from a resistor in a parallel circuit, we also have used metallic controls for cathodes, either aluminum or iron, which have not shown excess heat, but that allows us to put one additional control beyond just heat itself. I mentioned the thermal waveform reconstruction, and I'll show you that now. Here, for example, is the electrical input to an ohmic control. And when we try to calculate the heat that's generated, we find the following. If we use classical Newton's method, the best we can do is mark with the N. And that's because we have only T1 minus T2 terms. I don't use a bath because each ring has a number. So the first one is T1 minus T2, T2 minus T3, and we watch the heat move out. We find, however, if we add the heat of the barrier between the rings, then we come very close with the sum of being able to do a reconstruction, and we feel more confident with the results. This is the typical solution that we look at. The total carbonate level is 5 millimoles per liter. And we actually use fairly low levels of ionic strength. This is fairly close to air equilibrated distilled water. And we allow it to move down from an initial resistivity of approximately 18 megohm centimeters down to just under 1 megohm per centimeter before we use it. As I said, we've tried wires, woven electrodes. Here is a multiple spiral cathode where each of these 2 have been removed to look for radioactivity after the experiment was done. But what we end up creating is what we call a multi-gauge multiple cathode. And these are spiral wound electrodes. The bottom is a coaxial system where, I'll talk about it later, we have a outer coaxial cylinder of gold and an inner wound nickel spiral. And that's just, here's some results. This graph has 4 curves on it. These 2 solid curves are the energy and are read off the right side axis. The remainder of the curves are power and are read off the left, which is a log scale. Over here is the time axis, and you can see that at the beginning we gave 10 hours in order for the system to reach equilibrium. We measure the noise levels and always try, I find this very important, of course, because if you drive the system below the noise level, you'll measure the noise and you can get pseudo excess heat. So we rule that out by measuring the noise level. Here we see the noise level fall from approximately 10 milliwatts to a few milliwatts. Here's an ohmic control and two more ohmic controls, and these are actually two nickel cathodes, two separate nickel cathodes within the same electrochemical cell. And what we see here is, in fact, the thicker lines is the input, and this is the observed output. So in the case of the ohmic controllers, we get back less out than we put in each of the three cases. However, in the case of the nickel light water system, when we correct for noise and we monitor it, we're getting more out than we put in. Now we see this is not stored energy, because when we do the integral over time, we can find a superlinear rise in energy, and here we see several tens of thousands of joules. Notice, in fact, that the resistors, you can't see this one, it's too low, but these are matched in slope. You'll see it in the next graph even better. And we get a larger linear rise for the nickel cathode, because there we're getting excess heat. Here's a slightly different system. That last one was nickel versus platinum. This one is nickel versus gold. And I'll point out the differences and what we're doing in a second. Here again, we try to get an initial baseline. Again, there are four curves on this graph. The two solid lines here are energy and are to be read off the right in terms of tens of thousands of joules. And all of the remainder are watts and read off the left, which is a log plot. Here again, we measure noise, which begins at around 100 milliwatts and drops to about 40 milliwatts. The ohmic control, we're able to match the energy. And here we see a superlinear rise in energy. This is the input power to the nickel system, and we get more out than we put in. Each of these are separate input power drive levels. And this is where we got the development that there may be the possibility of an optimal driving point to these systems. When we look at the power gain as a function of input power for this system, which is, this one is nickel versus platinum, what we find is that the over-unity exists in a very small, relatively small input electrical drive area. And shortly later, we'll get into the reasons of this portion and that portion. Let's look at a few more of these. Here's another one. This is from the coaxial system I showed you. The only time this is over unity is over here. To drive it outside that range, for reasons we'll talk about, we do not see over unity. Here's some other electrochemical cells. The same thing occurs. We see a peak and down it goes. We've looked at this on a linear log plot. Here are two electrochemical cells. And this is pretty important because this may enable us to characterize any type of electrochemical system by considering not the average response, but maybe what the peak response is, if we could know where to optimally drive it. We believe that the use of this type of examination of materials may give rise to the development of an optimal gain that can describe any type of electrode system, as well as the way of knowing how to match your driving system to get that response. This graph shows a summary, or this is the first half of the table, showing the summary of our findings. For example, when we use iron versus iron, we never get excess heat. When we use platinum versus aluminum, no excess heat. When we do platinum versus platinum that has been contaminated with nickel, we do see low-grade possible excess heat, but very wide levels, so we rule it out. Nickel wire, we get very low level excess heat, and same thing with the platinum versus nickel spiral. However, I think what is most interesting here and surprising to us has been the impact of gold on the anode. And we'll get into this in a moment when we discuss corrosion issues at the anode, which is the known site of corrosion. We find that although platinum and gold are generally believed to be inert and remain in the anode, we actually see them electrode deposit onto the cathode, and I'll show you pictures shortly, And to my astonishment, it may actually be that these materials play a role in preventing the exit of the protium and perhaps other materials with palladium into the solution. And this may be the reason why we can get a definite energy gain as well as power gain. With consideration of these noise levels, these are typically the power by volume, power by area, and energy gains that we see for nickel-platinum systems. We believe that gold deposition during the experiment may have an important role on the cathode itself, and as I say also, we see the presence of an optimal operating point. In summary, and I'm not done because we're going to talk about the corrosion issues and where the heat comes from in a second, but from the enthalpic portion, we do see power gain with nickel-platinum systems with light water in the range of 10% to 300%, with a much greater improvement by using gold as the anode. It's not energy storage, as I've shown you. We measure the noise power, we do the integral over time, and in fact, we do see energy gain as well. Now, where does the heat come from? I hope this shows up. This curve, this graph, has two curves on it, and the remainder just shows where the heat appears to be coming from. This red graph here, I'm leaving the other dots, the other experimental points out, are one of these optimal operating points, which we used to call the pine march in some of the literature because we were trying to minimize electrolysis. I mean, otherwise it would have been a peak. But our goal was to get the, at the time we were working with palladium, the goal was to get the hydrogen isotopes into the metal, which would mean, because it's mutually exclusive, not to get it into the exit gas stream. What's interesting here is, if you look at this curve, which is the relative temperatures of anode to cathode, so that if we're above this line, the cathode is hotter. If we're below this line, the anode is hotter. We see the following. Now, this was our only experiment we've done so far. It's not been repeated. It's what we're looking at now. By use of the intercell differential temperature measurements, at the point of the optimal operating point, we find that the cathode is the site of the heat. When we move beyond that, the anode becomes the site of the heat, consistent with recombination at that platinum electrode. And of course, before the optimal operating point, the heat seems to be equally distributed between anode and cathode. One thing that has come out of this study is that the anode is not inactive. And as I say, can deposit materials, and perhaps for good use, onto the cathode. What we find is that in brown materials, when we use gold as the anode, is deposited, which we believe is consistent with boric hydroxide. In fact, corrosion issues are a major problem in these studies. I apologize for this. These bottles in the color pictures are green. When the nickel goes to nickel hydroxide, it's a beautiful green flocking that you can spin out. And that's what these bottles were showing. See, here's some fiber excess that initially occurs. And then when we end up treating it, using it as the anode, of course, it all dissolves into solution. And that's why people end up switching to platinum and gold, which still end up depositing a bit. We can actually see the gold on the surface. I hope this shows up. As a brown, golden colored material deposited over the nickel. One question we have is this a general phenomenon? And we think it may be. Dr. Miles and Spock were very helpful and lent me some of their data. And what we did was go back over the information to try to determine the electrical input power. And we find the following. Here we see 5 curves, 5 disparate experiments. So We're looking at relative amounts, and don't try and compare helium to heat. We're just trying to see what overlaps. When we do this, we see the following. Here's the nickel data with excess heat. Here's the excess heat for palladium from Dr. Miles' data. And here we see the production of helium, the same. This is the appearance of what it seems to be an optimal operating point for the palladium system as well. And here's Dr. Arata's work, which we believe is separated by an IR gap here. And these are the production of tritium from Dr. Spock's data. This is palladium in LiOD, and this is with co-deposition. So it may even be that optimal operating points are separated, and the products that one sees may be dependent on where you bias your system. Now, where does it come from? We think that the etiology of this biphasic response, this optimal operating point, may be due to limitations of loading, perhaps surface impurities, perhaps the kind of delay of loading on the upslope. On the downslope, we believe it to be competition with gas exit stream loss. The fact that once you end up getting bubbling, you're going to put most of your input electrical power up to the gas stream. In fact, we have seen that as follows. This graph shows on one of this is one of the this is 8 cathodes wound around opposite goal. And what we find is that by increasing the voltage very slowly, actually we're using a current source here, but as we're increasing the voltage very slowly, all of a sudden we get large bubble formation. And now we have a new curve that we move to. So here we start working on the system, and we start raising the current source from nanoamperes up to milliamperes, and at some point we get large bubbles forming on the nickel, and we come down to a new operating curve. I think we want to be right here. In looking at the nickel, we see no evidence of residual radioactivity. Here's the background when it's stripped off. Here are 2 of the nickel electrodes. It's absolutely flat, which leads one to conclude that perhaps deuterium is a product, but I have no way to prove it. Let me now summarize. We see excess heat in the range of 10% to 300% for nickel versus platinum, 200% to 900% for nickel versus gold. It's not energy storage, and we see energy gain as well. The optimal operating points appear to be fairly reproducible. They generalized behavior. It may be due in part to changes between the surface, competition with gas exit loss, and possibly even with the breakpoint that I showed you in the drive system. Our peak power levels were 7 watts per cubic centimeter, 88 milliwatts per square centimeter in nickel. I've got a lot of people to thank for helping with this.
Well, this paper is a very fine paper. Is open for discussion. Dr. Morrison.
What is the source, the origin of the energy you're observing? Is it a nuclear reaction, fusion, or what?
I have no evidence of a nuclear reaction because I looked for gamma emissions at those metacritics. We did not do simultaneous measurements. I'm not sure what the origin is.
So it must be somewhere.
Pardon?
I mean, if you believe in conservation of energy, the energy must come from somewhere.
Well, I certainly believe in conservation of energy, and I do believe cold fusion will be explained by conventional physics. What I can't rule out is the production of deuterium as the possibility of these reactions. Other than trying to do a mass measurement, which we've tried, and is well below our sensitivities because of problems with separation factor, I think it's very difficult to tell right now.
But if you produce deuterium as a problem, because it's proton-proton giving deuterium, then you conserve charge, so you must have a positron. And the positron will annihilate and you'll see the gamma rays.
Okay.
I think that point can be discussed around the poster. We have a question from the back, please.
Brendan Hall from Kine Allen. I was wondering if you got the heat after death phenomenon for the gold or platinum anode.
I'm sorry, I couldn't hear.
The heat after death phenomenon.
Never seen heat after death, no.
I think I'm translating an Antipodean accent.
No, in each case, we've been able to, as I showed you, in fact, let me show you, because that's important. In each of these cases, we always see that the observed heat comes down to the noise level. I've never seen any heat after death in there.
I'm Robert Briggs, and I'm curious as to the repeatability of your gold nickel experiment.
We find it relatively reproducible. Our biggest problems now are we've tried to minimize the mass, and we've had problems with destruction of the electrode, as I pointed out. We believe it's relatively reproducible.
In how many tries out of how many do you get exothermic reaction?
With gold?
Yes.
More than half.
Very good.
Thank you very much. We should thank Dr. Swartz again. The next and final paper of this morning's session will be presented by Dr. DeNinno of ENEA, Frascati in Italy. She will talk about cold fusion at ENEA, Frascati, a progress report on the work of the laboratory there.
I will present the progress report on the work made at Frascati ENEA by my group. First of all, I want to start to talk about the summary. We started from the working hypothesis, and then we planned our experiment in order to verify if this hypothesis is correct. We studied the influence of dynamic and metallurgy on the loading process, and then we passed to study thin films in electrolysis, and we tried to scale up the heat excess that we measure with a single film. And then I want to say something about the helium-4 detection system that we built in Frascati and is still under test. First of all, our working hypothesis. We started to study the hydrogen system, hydrogen metal system. As you know, hydrogen dissolves in metals and expands the lattice. It occupies the interstitial sites and expands the lattice, and in palladium, this expansion is up to 10% of the lattice parameter. This process generates very high stress fields when there are remarkable gradients inside the metal. And because of the diffusion coefficient is very low in palladium, there are, every time that you try to load hydrogen positive in palladium, you have very high concentration gradient inside, and then very high stress field. During the phase of coexistence between alpha and beta phase, there are very high stress fields on the boundary of the grains, and the stress fields can be so high as to induce plastic deformation inside metal. If you avoid during the loading the coexistence of alpha and beta phase using a procedure that Dr. Adami explained before, you can reduce the yield stress of the metal up to 50%. We hypothesize that stress field can inhibit the hydrogen diffusion process, and we try to imagine strategies to avoid this problem and to check if the hypothesis is correct. So the strategies that we imagine are to modify the loading dynamics, trying to avoid the growth of high concentration gradients, and then to prepare a material with a suitable microstructure to minimize the concentration gradient of the solute inside the lattice. So we started to study the influence of dynamic of loading on loading process. We tried two approaches. First, to limit the concentration gradient load. You can do this just loading very, very slowly your sample. but the diffusion coefficient is very, very low. It's something in between 10 to minus 8, 10 to minus 7 square centimeters per second. Or you can try to avoid the coexistence of alpha and beta phase and look what happened in this case. The second approach is to try to relieve the stress that are anyway generated inside the metal through something like anode stripping during electrolysis, I mean to reverse the polarity between anode and cathode, and look what happened. This is the results we obtain if we try to load in different way similar cases of palladium. The first one, the sample, is loaded just in electrolysis with any preloading of nothing special, just put inside the electrolytical cell and look what happens. This is a typical loading. This is the air on air zero ratio. This value here means that our sample goes up to 0.67, 65, 67. It is 65 or 70% of deuterium inside the sample, and nothing more happened in days. The second sample, B sample, was preloaded in gas, trying to skip the coexistent phase, just going up to the critical point of deuterium in palladium. It is 34 bar and 270 Celsius. Using the procedure shown before by Dr. Azami. Something like this. These are the isotherms. This is the pressure, this is the concentration. This is the isotherm of the system deuterium in palladium. You can go over the critical point with the trajectory like this one. And then you obtain, again, the beta minimum phase, the beta minimum value, because it's a stable point, but you avoid the growth of the beta phase inside the alpha phase, because beta phase grows like as bubbles inside the lattice. So in this case, we obtain a very different behavior of the loading. And at the end, a higher loading ratio. The difference between the loading is not so high, it's not so important, because in this case we obtain something like 0.8. In this case, 0.7 is not this is the point. The point is the different dynamic that we obtain in this sample. In this case, we go over the maximum of the air on air zero curve, and then we go to a minimum, and then the sample lose the excess of deuterium again. So something is happening inside the sample. This is the meaning of this behavior. In this case, nothing more happens about the minimum, the stable point, the beta minimum point. That means 0.7. So it's a different situation. So this means that just changing the procedure of loading, you can obtain different results. You can transform different materials. Then we started to study influence of microstructure on material, and we studied influence on concentration, so short-circuit paths. We started from a basic hypothesis that was, okay, the diffusion coefficient is very high in the boundary between grains. So if we have very small grain size, we have a lot of boundary. In this case, it must be easier to have high loading ratio. So we try to test if this hypothesis is correct. We imagine the process to go on in two different steps. Firstly, hydrogen is incorporated in a grain boundary network where the diffusivity is higher. It permeates the material without generating a big stress. And in the second step, it's incorporated into the grain bulk. The diffusion and the boundary acts like as a source. What is important, what we thought, is that if the volume is small, the energy associated to the elastic field is small because it's proportional to the volume. But what we found it's not exactly what we expected. This is the experimental procedure that we use. We perform different thermomechanical treatment. We use cold working, just by rolling, and then the thermal treatment of the sample, scanning the temperature, range, and the time of each treatment. We prepare 3 different batches, starting from a single piece of haladi, and we reduce the thickness to 3 different thicknesses. This induces a different lamination rate in each of the 3 pieces. Then we cut it again, and we scan the temperature in a certain range. Then we analyze the microstructure obtained through the scanning electron microscope and measure the grain size on the backscattered electron images. What we found is this, and is that there is a maximum in loading ratio versus the thermal treatment temperature. What does it mean? The thermal treatment has the effect just to increase the grain size. It is well known from literature. You can see here. Nothing new, but this is a sample, the same sample, treated at 800 centigrade. This is the same at 900, and the grains are bigger for 1000, more bigger for 1100. And in this case, you can see some recrystallization. That means that the grain boundary are bigger in this case. Something new is happening in this phase. It is well known. But we started from samples which had a different mechanical treatment. And this means that the grain size is related to thermal treatment temperature through a linear relation, but with different slopes. And the slope depends on the hardness of the material that you induce with the mechanical machining. So, the effect of machining on loading ratio let us correlate the maximum loading ratio achievable with each sample to the grain size. And we obtain the maximum. This means that our starting hypothesis was wrong, because if the smaller is the grain size, the better is the loading. You should have had behavior like this, where straight line with the negative slope, with the maximum for very small grain size. It's not the case. We have maximum. This means that there is another phenomenon. There are 2 phenomena concurring to this to generate this effect. So it can be observed that each value of thickness reduction by cold rolling, there is a presence of a maximum. And we think that this is due to 2 factors. A smaller grain size will reduce the strength of the stress field at the sample surface, because the grain boundary network plays a leading role for the fast diffusion of hydrogen inside the lattice. But the softening of the mechanical properties induced by the larger grain size can activate the stress relief mechanism. I showed yesterday in the poster a picture obtained by scanning electron microscope, in which it was possible to see that only the bigger grain size show some relaxation waves that are not present in very small grain size. So we found that there is a better range of the grain size that allows to attain comparatively high loading ratio. That means that this range is from 50 to 60 microns. There is another effect that we would like to study, and is that the grain size after electrolysis is enhanced by a factor ranging from 1.5 to 2. I don't know exactly what that it means, but it means only that the sequence of the metallurgical steps leading to the transformation of the palladium. So you start with a piece of material at the beginning of the electrolysis, but then during the electrolysis, the modification that you induce through the dynamics and through other phenomena that are not well known can lead you to work with a completely different material. And the combination of all the effects can easily explain the lack of the reproducibility which is characteristic of this kind of experiment. But the main goal of this research is to improve the reproducibility of ICCF experiment. So we did some experiments to prove if a good reproducibility corresponds to a high loading ratio. The statistics is very poor, but we obtain a significant improvement in the reproducibility. Here I reported 6 tests, and in 4 out of 6 we observed an excess when the loading ratio was greater than 0.92. I know that this is not proof because the statistic is not good, but just an indication. But moreover, we sent an electrode prepared in Frascati at SRI, and they found quite similar behavior in XSE. I want to focus your attention on the fact that the XSE is very small, in the order of 200 to 300 milliwatts, that correspond to less than 10% of the total power. But it's very clear. It's very clear, and it looks the same from one experiment to the other. And it is important because in some way it is reproducible. Then we want to see if our hypothesis is correct going towards thin films. Because we want to test if low dimension can help in the stress relief. We started using a nickel substrate because nickel seems the best metallic substrate to have palladium hydride preparation. Palladium and nickel has the same lattice structure. They are both FCC structure. They are almost the same lattice parameters that allow to obtain epitaxial growth on the surface. They both expand their lattice by dissolving hydrogen inside. And the difference, we hope that the difference between the strains can help in reducing stress at the boundary between the film and the substrate. The basic idea is to let the film to relax the stress toward the substrate. If you have if you have a substrate that is too hard, this is impossible. You have to choose a substrate that in some way follows the loading and the deformation of the palladium film. This is what we did. We prepared nickel plates, 100 micron thick, coated with palladium. Palladium film was obtained by thermal evaporation without particular care in cleaning the surface of nickel, I mean without press patterning or chemical etching. In this case we have a problem. Because they are both metal, it is impossible to measure in real time the loading of the material through the technique of electrical resistance. We can just measure the resistance of all the pieces, nickel plus palladium, and we can discriminate between the two contributions. However, we can say that even if the nickel is coated by palladium film, its resistance versus the cell current during the electrolysis is increased. So the situation is not worse than in the case where nickel is alone in electrolysis. It is not too much, it's just an indication that allows us to say that in some way palladium lets the hydrogen or deuterium to enter and pass through the field. And we measured the excess heat of this kind of system. We did 5 or 6 experiments, just measuring the excess heat. We have no correlation with the load in this case. And we found a very good reproducibility. And what is important is that the excess heat versus the ratio of the resistance is very reproducible. I mean, this is an exponential curve here, and it is possible to interpolate the curve with an exponential that has always the same parameters for every experiment. This must be significant because this number here, R0, is related to the electrolytical current. So what I want to say is that there is a relation between the excess heat and the current in the cell that is very reproducible for this kind of experiment. The excess heat is also in this case is not so high, in the same range. It is 250 milliwatts, but again it's very clear. Then, next step to convince people that this is a real effect is try to scale up the system and to see if it's possible to produce more excess heat. We realized a multiple cathode cell to see if the excess power is multiple of the one measured in a single cell. I mean, if I have 200 milliwatt with only one cathode, is it possible to have 400 milliwatt using 2 cathodes? It's very, maybe late, but the configuration that we use is a set of parallel electrodes, cathode, cathode, this way. Something like this. There are a lot of problems in this case because the geometry is very complex from an electrochemical point of view because it's very difficult to know the primary current distribution inside this object. It's parallel of resistance, but only at first glance because we don't know exactly what is the distribution in the different branches of this parallel. So we don't know exactly if the different electrodes are working in the same way. What we obtained in the very first test that we did is this. This is the excess heat for the single cathode cell, and white one is the excess heat for a cell working with 2 cathodes. The excess heat is higher. It's more than double. But it's very, again, it's a small but clear indication that something happened. It goes in the right way, in the right direction. There are a lot of problems in this case, in this kind of experiment. The comparison between double and single cathodes show an increase of excess heat measure. However, it's very difficult to correlate the excess heat to the current because I don't know exactly what is the splitting between branches. Then there are unsolved problem with the film adhesion on substrate. The electrolysis lasts only a few days, at the end of which the palladium films goes down, becomes powder. And we think that scale up the system is probably the best way to persuade the skeptics on the reality of heat excess production. Then, I want briefly to say something about the detection of helium-4 gases from the electrolytical cell. We choose a method that is quite different from the other I heard yesterday example. We accumulate gases evolving from the cell in a small volume that contains a catalyzer. So we have an external catalyzer, external from the cell. After the catalyzer, the catalysis cell that is made out of glass, everything is made out in stainless steel or metal. Everything, I mean, salt fittings, all everything. And then we expand the gas in a volume containing activated charcoal at 77 K, eliminating water vapor, oxygen, and other condensable. Then there is a ultra-high vacuum chamber in which there is a mass spectrometer and a getter pump, which eliminates everything but noble gases. So at the end, we have in the mass spectrometer chamber only helium, neon, argon, nothing more. This system allows us to set a lower limit to our measurement, which is 10 to the 13 atoms that are due to the pollution of the environment, of the helium contained in the air. So we are able to see helium for production more than 10 to 13 atoms. We did calibration and we started to work with this very complicated object, but the results are very preliminary, so it's not too easy to tell you. I hope you next year. Thank you.
Thank you very much, Dr. DeNinno. Do we have some discussion? Professor Huggins.
I think this is very nice work, but it's very difficult to separate the kinetic effects of the presence of grain boundaries from the final composition effects. I agree with you that hydrogen, it's well known, hydrogen diffuses faster down the grain boundaries than through the bulk. But what you measure for loading is not the rate of transport of hydrogen into the material, it's the final amount of hydrogen. And that will only depend upon the grain size if you also have hydrogen located